By the third week, the thermal imbalance is no longer subtle. It's written into the very structure of the operation. The left side tap hole, always cooler, begins requiring longer tap times. The iron flows sluggishly, forcing the workers to keep the channel open for extended periods while the hearth drains. The slag, thick and viscous, clings to the runners and solidifies faster than the crew can manage it. They start bringing extra sand to bed the channels deeper to insulate against premature freezing. On the right side, the opposite problem develops. The iron comes fast and hot, almost aggressively. The first rush from the tap hole carries so much thermal energy that the clay plug sometimes fractures instead of drilling clean. The runners glow white at the edges. Slag separates violently, spitting and steaming when it hits the cinder pit. The crew learns to stand farther back to anticipate the surge. Production remains steady overall, but only because the two sides now require completely different handling procedures. What used to be a symmetric operation has become two parallel processes, each demanding its own timing, its own rhythm. The foremen start assigning specialized crews, left side men who know how to coax the cooler iron, right side men who can handle the heat. The structural consequences begin to manifest. During a maintenance window, inspectors find that the furnace shell has developed a measurable tilt. Not from foundation settlement, the base is level. Not from external loading, the support columns are plumb. The furnace itself has warped slightly, the brickwork compressing unevenly under differential thermal expansion. The right side, running hotter, has expanded more. The left side, cooler, has contracted fractionally. The result is a subtle but definite lean, barely perceptible to the eye, but clear in the survey measurements. The refractory damage accelerates on the hot side. What started as surface wear progresses to deeper erosion. The bricklayers patch it during a brief outage, installing new firebrick in the scoured sections. Within days, the new brick shows the same accelerated wear. Whatever is driving the temperature imbalance is powerful enough to override the protective properties of the lining. The acoustic signature becomes impossible to ignore. Workers in adjacent buildings can identify which furnace is running by sound alone. The divided tone carries through the ironworks like a signature, a sustained dissonance that marks furnace number 4 as operating in a mode no other furnace shares. Engineer Harding finally acknowledges the severity during a night inspection. Standing between the two tap holes, feeling the heat differential on his face and hands, hearing the two distinct roars merge into a single discordant sound, he realizes this isn't just an operational anomaly. It's a stable, alternative state. The furnace hasn't malfunctioned. It has transformed. He orders a controlled cool-down for comprehensive internal inspection. It takes 3 days to bank the furnace, let the charge burn down, and cool the interior enough for entry. When the crew finally goes inside with lanterns and plumb bobs, they find everything structurally sound. No blockages, no collapses, no warped plates or shifted tires. The geometry is correct. But the evidence of division is everywhere. The brick on the left side is coated with thick carbon deposits, the surface almost glossy. The right side is etched and roughened, the mortar joints recessed from erosion. A vertical line separates the two zones, running from the hearth to the throat, perfectly straight, as if drawn with a rule. The men measure everything. They check for draft leaks, for cracks, for any physical asymmetry that might explain the split. They find none. When they withdraw and the furnace is relit, the division re-establishes itself within hours. Left side cool and carbon-rich. Right side hot and oxidizing. Same feed, same blast, different fires. The escalation is no longer about operational inconvenience. It's about understanding why a symmetrical system has locked itself into asymmetry. Why the furnace prefers this divided state over the uniform combustion it was designed to maintain. Why, once established, the pattern shows no tendency to self-correct. The physics is doing something no one expected. And until they understand what, the furnace will continue to burn with two hearts, each beating to its own rhythm, neither willing to synchronize with the other. The explanations come quickly, each seemingly plausible until tested against the evidence. The first theory centers on charging practice. Perhaps the skip hoist is dropping burden unevenly, creating a heavier column on one side. The operators check the bell mechanism obsessively. They measure distribution patterns during charging. They photograph the burden surface through the throat inspection port. The charge lays down symmetrically every time. The coke and ore distribute evenly, but the furnace continues burning asymmetrically. The second theory suspects the blast system. Maybe one blowpipe is delivering more air than its counterpart. The maintenance crew disconnects each blowpipe in sequence and measures airflow with pitot tubes. Every pipe delivers the same volume at the same pressure. They swap blowpipes from left to right. The hot zone stays on the right. The cold zone stays on the left. The division isn't following the hardware. Sabotage enters the conversation quietly, mentioned first as dark humor, then taken seriously when rational explanations fail. Could someone be tampering with the furnace, adding material through an inspection port, blocking a tire intermittently? Management stations observers around the clock. They watch every approach, log every person who comes near the structure. Nothing. The furnace operates under constant surveillance, and the asymmetry persists. The refractory quality comes under scrutiny. Perhaps the bricks installed during original construction were of inconsistent quality, causing one side to insulate better than the other. The masons pull samples from both zones. Laboratory analysis shows identical composition, identical porosity, identical thermal properties. The brick isn't the variable. A more exotic theory suggests that magnetism might be involved. The iron ore might contain enough magnetic material to be influenced by Earth's magnetic field, causing the charge to drift preferentially toward one side during descent. The idea feels too strange to be true, but they test it anyway. Compass readings inside the cast house show no anomalies. A non-magnetic limestone in the charge shows the same asymmetric descent as the iron ore. The magnetic hypothesis collapses. The metallurgist proposes chemical imbalance. Perhaps the ore blend is inconsistent, with one batch running higher in certain oxides, affecting combustion character. They analyze the iron produced from each tap hole separately. The chemistry is identical. Whatever is dividing the furnace is happening downstream of the chemical reactions. Harding brings in a consultant from Pittsburgh, a furnace specialist who's worked on blast operations across 3 states. The man spends 2 days observing, measuring, questioning. He inspects the foundation. He checks the wind system. He reviews the charging logs. Finally, he admits he's never seen anything like it. His report concludes with professional understatement. The asymmetry is persistent and structurally stable. No apparent mechanical cause identified. Recommend further investigation of aerodynamic factors. Aerodynamic factors. The phrase sticks with Harding. Not mechanical, not chemical, not structural, aerodynamic. Something about how the air moves through the furnace once it enters. Something about flow patterns, about how gases organize themselves in a large, hot, vertical column. But blast furnaces are designed to promote uniform flow. The tires inject air symmetrically. The rising gases should distribute evenly through the burden. Combustion should be radially symmetric, with temperature varying by height, but not by azimuth. That's the theoretical baseline, the assumption underlying every aspect of furnace design. Yet theory and reality have diverged. The furnace is operating in a mode that shouldn't be stable, shouldn't persist, shouldn't resist correction. And every conventional explanation has failed to account for it. The workers continue their shifts, adapting to the division, learning to read its moods. They know how the left side will respond to a harder blast. They anticipate the right side's surge when the charge settles. The asymmetry has become familiar, almost predictable, but no one understands it. Harding stares at the consultant's report, at that phrase, aerodynamic factors. He thinks about air flowing through heat, about pressure gradients in confined spaces, about the way gases behave when temperatures vary by hundreds of degrees over short distances. Somewhere in the fluid dynamics of the furnace interior, something has organized itself into a stable division. The question is what, and more importantly, why it stays that way. The breakthrough begins not with theory, but with careful observation of the mechanical evidence the furnace provides. A young engineer named Samuel Croft, recently graduated from Lehigh, starts documenting vibration patterns. He borrows a seismograph mechanism from the college, designed to detect earthquakes, and adapts it to register vibrations in the furnace structure. He mounts sensors at 6 points around the base, equidistant from each other, and records the output over a full 48-hour campaign. The tracings show clear differences. The left side produces low-frequency oscillations at a steady amplitude, a rhythm that correlates with the charging cycle but persists between charges. The right side generates higher frequency vibrations, more chaotic, with sharp transients that spike during blast intensification. The vibration isn't random noise. It's structured, patterned, as if the furnace is resonating at two different fundamental frequencies simultaneously. Croft shares the data with Harding. Together they recognize something crucial. The vibration frequencies correspond to the acoustic tones everyone has been hearing. The deep hum from the left side is mechanical resonance in the lower registers. The higher roar from the right is turbulence-driven oscillation. The furnace isn't just burning asymmetrically, it's vibrating asymmetrically, locked into two distinct modes of acoustic behavior. The insight prompts a new round of tests focused on airflow. They rig smoke generators at the tire level, injecting visible tracers into the blast stream to observe how air moves through the burden. During a brief reduction in blast pressure, they send smoke into each blowpipe and photograph the patterns visible through inspection ports. The results are stunning. The smoke doesn't diffuse uniformly through the charge. It follows paths, distinct channels that organize themselves within minutes of injection. On the left side, the flow spirals upward in a slow, coherent helix, maintaining laminar character for remarkable distances. On the right side, the flow fragments immediately into turbulent eddies, churning and mixing violently. Two flow regimes, two combustion characters, two acoustic signatures. The correlations are too consistent to be coincidental. They measure pressure differentials next, installing manometer taps at multiple elevations on both sides of the furnace. The readings reveal something unexpected. Despite symmetric blast delivery at the bottom, a lateral pressure gradient develops higher in the stack. The right side consistently measures 8 to 12 inches of water column higher pressure than the left at mid-height. The difference diminishes toward the top and bottom, maximizing in the central combustion zone. Harding sketches the implications. Pressure gradients drive flow. If pressure is higher on one side, air will preferentially move toward the lower pressure region. But the air enters symmetrically at the bottom. So somewhere in the lower third of the furnace, the flow must be diverging, splitting, choosing sides. They inspect the burden structure by dropping weighted probes through the charge during operation. Dangerous work, but necessary. The probes reveal that the coke and ore have organized themselves into different packing densities on opposite sides. The left side, cooler and carbon-rich, has developed a tighter, less permeable structure. The right side, hotter and more oxidizing, has a looser, more open burden. The difference is measurable. Permeability varies by nearly 30% from left to right. But which came first? Did the thermal imbalance create the permeability difference, or did the permeability difference create the thermal imbalance? The question loops back on itself. The system is self-reinforcing. Hotter combustion creates more open structure. More open structure allows more airflow. More airflow intensifies combustion. Heat and flow and structure have locked themselves into a feedback loop divided down the middle. The acoustic measurements provide the final piece. Using tuning forks and resonance detection, Croft determines that the furnace interior is supporting standing waves, persistent acoustic modes that organize airflow into stable patterns. The left side's lower frequency corresponds to a fundamental resonance mode of the entire chamber. The right side's higher frequency represents a harmonic, a faster oscillation that fits within the same physical space, but at a different modal frequency. The furnace has become a giant organ pipe, but one playing two notes at once. The resonance is organizing the airflow, dividing it into two stable circulation patterns that reinforce themselves through acoustic coupling. The air doesn't just flow through the furnace. It resonates, and that resonance determines where the air goes, how it mixes with fuel, how completely it burns. Harding assembles all the data: pressure gradients, flow visualization, vibration analysis, acoustic resonance, burden structure. The picture emerging is one of profound self-organization. The furnace hasn't malfunctioned. It has found an alternative equilibrium, a stable state where multiple physical processes, thermal, fluid, acoustic, structural, align into a divided configuration. The question remaining is, what triggers it? What pushes a furnace from uniform operation into this split state? And more practically, can it be reversed? With evidence accumulated, Harding assembles a formal investigation team. In addition to Croft, he brings in David Prescott, a fluid dynamics specialist from the Stevens Institute, and Herman Vogel, a combustion engineer with experience in European furnace design. Together, they plan a systematic measurement campaign to quantify exactly what is happening inside the furnace. They install thermocouples at 16 locations around the circumference and at 4 elevations. The wiring is complex, the installation dangerous, but the resulting temperature maps are revelatory. The data shows pronounced thermal stratification, horizontal layers of different temperatures stacked vertically in the combustion zone. But critically, the stratification is tilted. The isotherms aren't level. They slope from left to right, creating a ramp of temperature that rises by nearly 300 degrees across the furnace diameter. Prescott recognizes the signature immediately: lateral pressure gradients driven by density differences. Hot gas is less dense than cool gas. In a confined vertical column, density differences create buoyancy forces. If temperature varies horizontally, buoyancy will vary horizontally, and that generates lateral flow. The tilted temperature field is driving circulation, a slow, sideways drift of gases from the cooler side toward the hotter side. But why doesn't the circulation mix the gases and eliminate the temperature difference? That's what should happen in a convective system. Hot and cold should blend until uniformity is reached. The answer lies in the boundary layers. Vogel examines the refractory surface characteristics and realizes that the brick itself is controlling the flow. On the left side, carbon deposition has created a rough, insulating surface that disrupts flow near the wall. Gases slow down, spend more time in contact with cooling surfaces, lose heat. On the right side, the scoured brick is smoother and less insulating. Gases maintain velocity along the wall, retain heat, continue burning. The boundary layer behavior is different on each side, creating different heat transfer rates to the structure, which reinforces the temperature difference, which drives the lateral pressure gradient, which organizes the airflow, which maintains the boundary layer differences. Another feedback loop. They conduct a crucial experiment. During a planned reduction in production, they lower the blast pressure gradually while monitoring all parameters. As pressure decreases, the acoustic resonance begins to weaken. The toot and roar softens into something more uniform. The vibration patterns begin to converge. But before they can push the system fully out of the divided state, production requirements force them to restore normal blast. The divided state snaps back immediately. The system is attractable. Once established, it requires significant perturbation to dislodge, and it returns readily to the split configuration even after disruption. Croft builds a scaled model, a transparent column filled with strategically placed heaters and air jets, designed to demonstrate the principles they believe are governing the full-scale furnace. The model can't replicate the chemistry or the exact geometry, but it can show fluid behavior. When operated with symmetric heating, the flow remains uniform. But when they introduce a small asymmetry, slightly higher temperature on one side, the flow organizes itself into a stable division remarkably similar to what they observe in the real furnace. The demonstration convinces the team they're on the right track. The physics is real. The division is a natural consequence of coupled thermal, fluid, and acoustic processes in a large vertical combustion chamber operating at high temperature with confined airflow. Prescott derives simplified equations describing the system. The mathematics is complex, involving coupled differential equations for temperature, pressure, and velocity fields, but the qualitative behavior is clear. The system admits multiple stable states. Uniform combustion is one equilibrium. Divided combustion is another. Both are stable. Both can persist indefinitely. Which state the furnace occupies depends on initial conditions and history. The term bifurcation enters the discussion. In dynamical systems, bifurcation describes the phenomenon where a small change in conditions causes a system to switch between qualitatively different behaviors. The furnace has bifurcated from uniform to divided operation, and the divided state is now self-sustaining. Harding asks the critical question: can we force it back? Can we push the system through another bifurcation to restore uniform combustion? Vogel proposes a protocol: temporarily reduce blast pressure to weaken acoustic resonance, simultaneously introduce asymmetric charging, heavier coke on the cool side to equalize temperature, maintain the perturbation long enough for the boundary layers to reset, for the carbon deposits to redistribute, for the thermal stratification to level out. It's risky. Production will suffer during the transition. If the protocol fails, they might destabilize the furnace into an even worse state. But leaving it divided means accepting permanent operational asymmetry, permanent uneven wear, permanent two-regime production. Management authorizes the attempt. On a cold morning in March, they begin the protocol. Blast pressure drops. Charging becomes deliberately asymmetric. Every parameter is monitored continuously. For the first hour, nothing changes. The division persists. The acoustic signature remains split. Then, gradually, the temperature differential begins to narrow. The pressure gradient weakens. The vibration frequencies start to converge. Over the course of 6 hours, the furnace transitions through a chaotic intermediate state, temperatures fluctuating, flows unstable, acoustic tones warbling, before finally settling into uniform combustion. The division collapses. The furnace breathes with one voice again. The relief among the crew is palpable, but so is the knowledge that they've witnessed something profound. A massive industrial system, governed by deterministic physical laws, capable of occupying multiple stable configurations, switching between them through bifurcations that no one designed and few understand. The final report, compiled over the following month, presents a comprehensive picture of what divided furnace number 4 and why the division persisted for weeks before intervention restored uniformity. At the core of the phenomenon was thermal stratification inside the combustion chamber. In a blast furnace operating at high capacity, temperature doesn't vary smoothly from bottom to top. It organizes into layers, horizontal zones of relatively uniform temperature separated by transition regions where temperature changes rapidly. This stratification is normal, but in furnace number 4, the stratification became tilted. The tilt originated from a minor asymmetry in initial conditions, likely a slightly uneven charge distribution on a single shift, combined with a momentary imbalance in tire performance. This asymmetry created a small lateral temperature gradient. On its own, convection should have eliminated this gradient within hours. But the lateral temperature gradient generated a lateral pressure gradient. Hot gas, being less dense, exerts less pressure than cool gas at the same elevation. With the right side running slightly hotter, pressure there was fractionally lower. This pressure difference, though measured in fractions of an inch of water column, was sufficient to bias airflow. Air entering through the tires naturally flows toward lower pressure. The slight pressure gradient caused a subtle drift of combustion air from left to right. This drift intensified combustion on the right side while starving the left side, amplifying the original temperature asymmetry. The feedback loop was established. Simultaneously, the acoustic environment became critical. The furnace, like any large cavity, supports resonant modes, standing waves of pressure oscillation. At normal operating conditions, multiple modes are present simultaneously, creating complex interference patterns that average out over time. But once the temperature field became asymmetric, The acoustic environment split into two dominant modes. The cooler left side supported a lower frequency fundamental resonance, a deep tone corresponding to the full height of the chamber oscillating slowly. The hotter right side supported a higher harmonic, a faster oscillation fitting within the same space, but at a different modal frequency. These two modes organized airflow into distinct circulation patterns. Air on the left spiraled upward in phase with the slow resonance. Air on the right churned with the faster harmonic. This acoustic bifurcation locked the flow patterns in place. The resonance organized the air. The organized air sustained the temperature difference. The temperature difference maintained the resonance. The system was mutually reinforcing at multiple levels. Boundary layer separation along the refractory walls added another reinforcing mechanism. On the cooler left side, carbon from incomplete combustion deposited on the brick, creating a rough, insulating layer that slowed flow near the wall and reduced heat transfer to the structure. On the hotter right side, complete oxidation kept the brick clean, maintaining high heat transfer and allowing gases to flow faster along the wall. The burden structure responded to the thermal field. Hotter zones cause more complete combustion, which consumes coke faster and creates a more open, permeable structure. Cooler zones preserve coke longer, creating a tighter, less permeable structure. The permeability difference reinforced the airflow bias. More air went where structure was open. Less air went where structure was tight. The burden organized itself to perpetuate the division. What emerged was a state of coupled instability stabilized by multiple feedbacks. No single mechanism was sufficient to maintain the division. But together, thermal stratification, lateral pressure gradient, acoustic resonance, boundary layer behavior, and burden permeability, they created a stable alternative equilibrium that resisted perturbation. The system demonstrated a characteristic of complex nonlinear processes, multiple stable states. Uniform combustion was one attractor. Divided combustion was another. Once perturbed into the divided state, the system remained there until forced out by deliberate intervention. The engineering implications were significant. Blast furnaces could no longer be assumed to naturally maintain symmetric operation. Operators needed to monitor for early signs of division and intervene before the split became entrenched. Design modifications could help: better blast distribution, improved burden charging systems, damping of acoustic resonance through refractory design. But no design could eliminate the possibility entirely. The physics was fundamental. Other ironworks reported similar phenomena once Bethlehem published its findings. Asymmetric furnace behavior was more common than recognized, often attributed to mechanical defects when the true cause was aerodynamic self-organization. The Bethlehem investigation provided a framework for understanding and managing these states. For the workers at Furnace Number 4, the division became a story they told new hires. The time the furnace split itself in half, burning two fires in one stack, until the engineers figured out what the air was doing inside. It was a reminder that even massive, well-understood industrial systems could surprise you, could find ways of operating that no designer anticipated, governed by physics that didn't reveal itself until conditions aligned just so. The furnace ran uniformly after the restoration, but everyone who had worked through the divided period remained alert for signs of recurrence. They listened to the tone. They watched for thermal asymmetry. They understood that the division was always possible, always latent in the physics, waiting for the right perturbation to bring it back. The air could pull itself apart again, but now they knew how to pull it back together. And they knew why it happened. Thermal stratification creating lateral pressure gradients organizing airflow through acoustic resonance, resonance bifurcating the combustion into two stable regimes sharing one stack. The furnace that pulled the air apart had taught them that symmetry, once broken, doesn't restore itself. You have to understand the physics. You have to force it back. That understanding, hard-won through weeks of observation and careful investigation, became part of the operational knowledge of the ironworks. a lesson written in temperature differentials and acoustic tones, in asymmetric wear and divided flames. The furnace breathed as one again, but the memory of its division remained.